It's our pleasure to have Matthias Wilhelm from University of Southern Denmark. And he's going to tell us about some machine learning applications to ING physics. Take it away, Matthias, and thanks.
Thanks a lot. Thanks for the nice invitation to speak here. It's great to be talking to you, and I hope to visit in person as well at some point. I would really like to tell you some story about how we can apply machine learning for these analytic calculations that we are doing in the high energy theory community. And this is making it really much closer to machine learning, also of mathematics. So what I'm going to focus on today is a paper together with Matt von Hippe that we put on the archive now almost 3 months ago. But there has been quite some development on the archive since then. So 4 days after our paper appeared, there was another paper by 5 authors around the world, but originally Chinese, which were applying really, really similar techniques. And then last month, there was a third paper by Mao Zheng, which was applying different approach, but still to the same problem. And I'm also working on following up on this first paper together with Justin Behrman from Michigan and François Charton from Meta AI. I will start giving you a short introduction to the problem in like very abstract terms, and then talk a bit about how it occurs in the physics context. And I understand you're all high energy theorists, so I'll try to make this part a bit shorter. And then I'll go to 2 particular machine learning approaches that we tried on this problem, finding good success, before concluding and giving a bit of perspective on what can happen in the future. So in general, we are wanting to apply machine learning techniques in high energy theoretical physics. And the obvious question is, when can we do this? And I want to argue, and I'm looking forward to hear your opinion on this and your take on it, is that it's most useful or maybe most easy if we have a case where there's solutions that are hard to calculate but easy to check. So this is typical NP-hard problems. So typically, if you use something called ansatz anyway, you can instead try to teach the machine to make a guess or a heuristic for you, and then check whether it's correct. So first case for this that I looked into and am still looking into together with a bunch of people is this symbol bootstrap that we mentioned a bit in the conversation before the start of the seminar, where you have infinitely many constraints that your answer might will need to satisfy. So you might as well ask the machine to find a solution. A second really cool application is by Cliff Zhang, Jersey, and Matt Schwartz. And what they are doing is simplifications of spin-helicity variable expressions. So also with spin-helicity, if you know what they are, you know that there isn't really an algorithm to simplify them, find the simplest expression. But if you have 2 expressions, you can just plug in numbers and see with integer number accuracy whether the 2 expressions are the same. And if you do this for 10 different kinematic variable choices, then you can be pretty sure that they are actually the same. And the third one is integration by part reduction. And this is what the present talk will be about. So let me briefly give you the condensed version of the problem. And here I could have also given my talk the alternative title, Machine Learning for Linear Algebra. Now, if you know about linear algebra and machine learning, you might wonder, why could this possibly be a good idea? Linear algebra is linear algebra, and machine learning is, in a way, nonlinear optimization, so it's supposed to be much harder than linear algebra. But let me argue that indeed we can usefully apply it here. So really boiled down, the problem is that we have a large set S of redundant linear equations. And what we want to do is to pick a small subset that still allows us to uniquely solve for a given set of unknowns. Now, the challenge is that the number of subsets of this set is 2 to the number of elements in the set. So you can immediately see that you don't want to like enumerate all different choices. This is death by combinatorics. So you need some heuristics. And this is where machine learning comes in. It allows you to scan over different heuristics more quickly. So now let's come to the physics context. Unless there's any questions on the part already. I wanted to say this earlier, but please ask questions all the time. I would like to make this as interactive as possible.
So maybe I can ask a question for clarification. Are there versions of this challenge that are already implemented in some kind of problem where machine learning is has shown to be useful? I guess.
Yeah. In the high energy theory HeI community, at least in my corner of it, it's not fully functional yet.
Okay.
So, I mean, here with the first one, we have got a proof of principles. And the spinosilicity simplification, this is online. So they have an example notebook. You can play around with it. But there was also a paper by Ben Page and friends sometimes earlier this year, where they still used like old school methods, although being aware of this code. So it's not clear whether it's actually working at the scale required for state-of-the-art applications. And here, also for the last one, I would argue we're still at a place of a proof of principle, and more research is required. But yeah, I mean, the first paper on this was 3 months ago. And I think there's a lot of activity that I'm aware of, and most likely also some that I'm not aware of. So I think this is a very promising direction. There will be something. I would be surprised if it takes more than a year or two.
I see. Okay. Thanks.
Thank you. Of course, there's other areas like more numerically involved areas where they are solving Einstein equations, or where they are looking at the landscape of string theory compactifications, and sometimes also looking at improving numerics for numerically evaluating Feynman integrals. But what these things here have in common is that you really want to do analytic calculations.
I see. I see.
And this is yeah, I mean, it's a bit different from a general noisy setup in machine learning where you deal with noise and you deal with float numbers. Whereas here, I mean, we really care about the exact solution, and we don't use linear regression typically, but phrase it as a classification problem. So 1 is not closer to 2 than to 100,
Right.
but the solution is either right or wrong.
I see.
And
I
it's
see.
exact, which is making it maybe more challenging than other areas.
I see. I see.
Okay. So physics-wise, I
Sorry,
think
can I also ask? So
yes.
your question was like you have this very large set of linear equations. So in principle, you could just pick one of it and solve it in terms of one variable, and then replace it in all the other ones. And then at some point, some of them will be zero equal to 0. And but so the problem of this is that you have to do simplifications. I guess if you have you're thinking of a problem where you have a huge amount of variables, and then when you do these replacements, things become complicated. Is that and
so here we're using the approach where you're doing the just picking a set and you see whether it works, yes or no. But yes, there's the possibility to pick one equation at a time. And this is what Mao Zeng is doing. So this is the paper I mentioned in the title here. This is the paper from last month by Mao Zeng. But also there, if you want in solving with Gauss's algorithm, is still depending on the order in which you apply these steps. And then you have the permutation group. And the permutation group isn't fun either. So you also have too many possibilities to just enumerate them all. But really, what you suggest of just picking one, picking the next, and seeing where it goes is what Mao Zeng did in his paper from last month.
I see, but so you're anyways trying to find a way to make this as easy as possible. So you pick the equation such that when you solve that one instead of the other one, the replacements are easier or something in on this line.
Yeah, or just there's less equations.
Or okay.
So in general, the less equations there are, the quicker you can solve them. And then, I mean, we have infinitely many equations, and some of them connect unknowns that we don't care to other unknowns that we don't care. So if you can avoid including them, it's better because you don't have to solve for something you don't care for.
Thank you.
Thank you. Okay, so with the physics context, I guess most of you are familiar that one of the quests in higher energy physics, we want to understand the laws of nature. And with the new experiments, both in the direction of high luminosity upgrade to the LHC, as well as to the third generation of gravitational wave observatories, we have in the future, in the coming decade, a lot more data that we want to see whether it agrees with our theoretical predictions. But this means we first need to actually calculate these theoretical predictions. And here, I guess, as most of you in your research, I'm using the framework of quantum field theory, combining special relativity with quantum mechanics. And the typical pipeline for calculations here, or at least the more traditional pipeline, works by starting with Feynman diagrams, named after Richard Feynman, and I guess you have all, or most of them, of you seen them, but they are looking like this. And if you are at loop level, you, for example, also have this diagram here with the loop. And then you need to do these integrals that are associated to Feynman diagrams. And in typical applications, again, this is all like order of magnitude, rule of thumb, you have 100,000, maybe a million, maybe slightly less different integrals, but they are not all independent. What you can actually do is reduce them to 10 to the 2-ish, again, different master integrals. And those master integrals, then you actually integrate and use to get your physical predictions. But this step to get from this 10 to the 5 roughly to 10 to the 2 is really the bottleneck of many state-of-the-art calculations, and it's working by what's called integration by part reduction. And this works by realizing that Feynman integrals form a vector space of finite dimensions. So we can pick a basis, which are what we call the master integrals, and then we decompose all of those 10 to the 5 integrals as linear combinations of the master integrals, where the master integrals would be these I, small I, which all have some coefficient that depends on the kinematics, so the masses and momenta, and the space-time dimension. And as mentioned, that takes a lot of compute. And in particular, in this cool paper from a year ago on for-loop gravity, these authors, using still, thanks to Johan, the most recent code available, still required something like 300,000 CPU hours on a cluster to do this IBP reduction. So if you're able to do this quicker, better, faster, more resource saving, you will get a lot of computational reach, making a lot of computations that are currently impossible accessible. Any questions on that? Okay. So Feynman integrals are having in general the form that I'm showing here. And we're looking at families of Feynman integrals. So we are having some indices here, A1 to n. And the integral itself is over d-dimensional space-time and L different such loop momenta, which are elements in d-dimensional Minkowski space. And then in the denominator, we have these particular factors, which are functions of the loop momenta and raised to the power AI. Now, in a Feynman integral, say this one here, I have these 3 propagators in this triangle. So I would have 3 of these factors, but in general, at higher loops, I can have more. And then here, having higher powers is a natural generalization, but also occurs, for example, if you have self-energy diagrams, bubbles, which you insert, then the propagator to the left and the right of the bubble is the same. So it occurs with the power 2. Now, integration by part identities tell you that if you have the integral of a total derivative of such an expression here, this vanishes. So usually we would expect a boundary term to arise from the integral of a total derivative, but here these boundary terms are guaranteed to vanish. So in order to have some scalar final result, we sum here over Minkowski indices. And here this Q is what's called an IBP vector. It's again some vector in Minkowski space, and it can depend on the case, but also on any of the momenta in your problem. And now if you do this derivative, let it act via the chain rule and product rule on everything here, you find that you can express the result again as a linear combination of indices of integrals of this type, where these indices may or may not get shifted by plus minus 1. So if you look at the chain rule, applying it then to the inside of one of these denominator factors here, you see that AI would be shifted by 1. Now, we don't know how to solve these integration by part identities for generic AI. So instead, what we do is we specify particular values for all of these indices A, and then solve them. And this is known as Laporta's algorithm. But of course, you need to pick some values here. And it's no coincidence that this is called big S as well as the original set I had at the beginning, because it's exactly the original set I had in the beginning, of which we want to take a particular subset. So this was a fairly general and maybe abstract. So let's look at an example, a one-loop integral, the bubble integral, which is arguably the simplest one-loop integral you can reasonably look at. So being a one-loop integral, we have one of these loop momenta here, k, which goes around this loop. And we take one of these legs here to be massive. So one propagator is k squared minus m squared to the power a1. And the other propagator is massless, so p minus k squared to the power a2. And p is the momentum going in here, and m is the mass. Then if you calculate these integration by part identities here for the choice of q being p, you get the first line, and k, you get the second line. And this is a fairly simple calculation. You can do it on with pen and paper. This is one of my exercises in my quantum field theory course, so the students can do it easily. You just have to apply the chain rule and a product rule a bunch of times and complete some squares. So then one choice of the master integrals is to pick 1, 1 and 2, 0. So 2, 0 would be a tadpole, 1, 1 is the standard bubble. And then I could ask you how to reduce 2, 1 in the spaces. And one way to do so is you pick a1 equals a2 equals 1 above. And then you take the difference of those two equations. Those terms here cancel. And those terms are exactly 1, 1, 2, 1, and 2, 0. So you can solve for 1 AI 2, 1 in terms of those two master integrals. But if I gave you the task to reduce 5,5, it would probably take you a bit longer by pen and paper to figure out what values of A1 and A2 you have to select here, plug into this equation to really connect 5, 5 to 1, 1 and 2, 0. Any questions so far?
So Is it clear that there are only two master integrals in this for this setup?
So here it's clear because you can do the calculation. But there's also a criterion using the Lee-Pomeransky presentation of Feynman integrals, which allows you to count how many master integrals there are to determine the dimension of this vector space. And then, of course, any choice is good as long as you pick linear independent integrals.
Right. Okay. Thanks.
Thank you. So how do we choose these seeds? How do we choose A1 and A2, or in general A1 to AN? There, our current best answer is to do some heuristics. And to do this, I need to introduce some notation. One is T. So if we have such a vector, such a lattice element, we count simply how many of these AI are positive. So this is essentially counting how many propagators you have. Then R is the sum of all positive ones. So this is the sum of all propagator powers. Then D here is the number of dots, if you want. It's the difference between the two. So typically, if a propagator comes with a power 2, we put graphically a dot in the middle of it. And this is why this is called D. And S is the sum of the negative AIs, or rather the negative sum of the negative AIs. So essentially, this is counting how many of these propagators aren't actually propagators, but occur in the numerator as irreducible scalar products, as they are called, because you need to include those to make the whole IBP reduction work. But okay, it's just some numbers. And based on these numbers, you can define different heuristics. One is called rectangular seeding. So there you pick all of those lattice points where R for the lattice point is smaller than a maximum value, and S is smaller than a maximum value, and those you can pick. Then there's another heuristic called Laporta's golden rule, which in addition to rectangular seeding also requires that the number of dots is smaller than a maximum parameter which you can choose. So this was the state of the art for some more than 2 decades. But then in a talk at CERN at QCD Meets Gravity in December 2023, Johan Usovich proposed further improvement to this golden rule, to the previously known seeding strategies. And it looks fairly non-spectacular, but has a spectacular improvement of the actual number of seeds that you have. So what Johan proposed was to also require that S is smaller or equal to T minus L plus 1, where L is another parameter which you can choose. Don't ask me why this is a good restriction. You need to really stare at these things for quite some time and be an expert, as Johan did and Johan is.
Sorry, I'm not sure if I understand. So you want now to count in practice the master integrals. Is this what you're doing? No.
What I'm doing is, here in this example, I told you to pick A1 equal A2 equal 1 and plug those values into those equations. And I was promising you that this is sufficient to solve for 2, 1 in terms of the master integrals.
Yes.
So now the question is, in general, if you want to reduce something like 5,5, what values of A1 and A2 do you have to plug into this equation to then get a long list of equations that if you solve them, you can relate 5,5 to the master integrals?
So you're fixing the values of, in the next slide, you want to fix the values of A's, and then that gives you the recipes of what to solve, like this.
So I want to fix the values of Rmax, Smax, Dmax, and L. And then this fixes some values of A. And then I plug those values of A into those equations. And then I can solve for the master integrals, the integrals that I want to decompose.
So you start with one integral that is parameterized by some A's.
Yeah.
And
so this
then,
integral has it has a 5,5.
yes.
And I then want to choose those values for Rmax and Smax such that this set contains at least 5,5, or that the equations which it generates contains 5,5. But moreover, I need enough to also allow me to solve for 5,5 in terms of 1,1 and 2,0. And this is some heuristics that work for suitable values of those parameters. And in particular, Johan showed that, this last one gives some order of magnitude improvements in the number of equations, and thus also in the time that it takes an IBP solver to solve these equations.
Okay, thanks.
Can I also ask something?
Yes, please.
So with this improved seeding prescription, you have this parameter L, which you can choose. So for some values of L, it's possible that the subset S3 won't be enough to solve all the equations.
Yeah,
right?
You need to pick good variables for Rmax, Smax, Dmax, and L. And typically you want to choose them such that your integrals barely contain your target integral, or contain it and a bit more. But Kira lets you choose, or requires you to choose these values. Fire starts with some small values and then increases the values until it reaches the point where it can reduce your integral.
I see. Okay, but okay, so it's still it's a matter of picking some specific parameters and seeing if it is enough. You must test this, right?
Yes. All of this is about good guesses.
Yeah. Okay, thanks.
And the reasoning of using ML is to speed up the finding of such good guesses. So, as I mentioned before, I don't know how Johan found this particular heuristic, but if we wait for the next Johan to find something, we might be in for a long time, because this was really like 23 years between Laporta's golden rule and Johan's improved seeding algorithm. So if you can use the machine to speed this up, this is a big improvement. And I should mention that this bubble integral I showed because I can explain the problem on slides. But we're really using this double triangle, which is a bit more complicated. So you see a bit more structure. There's 7 different A's. And this is also one of the cases Johan used as a benchmark in his talk 2023. Okay, the first approach we tried on this was funsearch. This is going back to some Google DeepMind paper in Nature from 2023. And if you want, you could call it solving problems by automated brainstorming. And you're brainstorming using the capacity of the entire internet, if you want, to find those better heuristics. Another way to describe it is that you ask ChatGPT to give you a solution to your problem. And ChatGPT, being programmed the way it is happy to oblige. But ChatGPT has no idea what your problem is. So you should rather ask it for Python code that solves your problem, because then you can actually check how good it is. And then you can prompt it with 2 previous versions that reasonably well solved your problem. And you can ask it to improve on those 2 versions and give you something back where you can then again check how good it is. And in a nutshell, this is what funsearch does. If you want it in the words of the authors, you start with a pre-trained large language model. So typically you don't want ChatGPT, but something that's fine-tuned for code generation. So we have been using the Code Llama, but the original authors used Google's Cody, but you could use also CodeStrel or any other model on the market. And then you prompt this with a couple of programs that work well and ask it to improve it. It gives you a number of different attempts. You evaluate them, see which ones work well, which ones work not at all or rubbish. And then you take the best ones and you integrate them in your program database, which you then again use to prompt the neural network in the next step. So if you want, this is a version of genetic programming. So genetic programming mimics evolution. You could think about it as like you want to breed a dog with black hair. So you took 2 dogs of the darkest hair you can find, and you let them have puppies, and you keep the puppies with the darkest hair, and you continue like that. So it's a bit different from supervised learning or unsupervised learning or reinforcement learning, because there's no entity that learns, if you want. There is no weights that are adjusted via gradient descent. So the puppy doesn't learn to have black hair. That's not something that puppies can learn, but you keep the puppies that have black hair or dark hair, and you breed by selecting those specimens. So another property of it is that it has Python code as output, and that makes it possible or easy-ish with this general approach to have something that you can really interpret. So you're not having a black box as you typically have with ML, but you have something you can understand. And by understanding it, you can also try to generalize it. And now the question is, what puppies do we keep? What's the fitness if you have some survival of the fittest? And here we choose minus the number of equations if the set of equations is enough to find a solution, and an additional term here, penalty term, if the set of equations isn't enough. What exactly you put as a penalty here isn't too important as long as you avoid local minima and you have something that doesn't work clearly separated from the things that work. And then as the starting point, we took here some Python code, as you can see, and that corresponds to a Laporta golden rule system with dmax equals 1. And this particular choice gives 2,148 seeds. And then we put it into funsearch, let it evolve. And after 2,400 generations, it was down to 92 seeds. And this is really the improved seeding strategy, or equivalent to the improved seeding strategy with dmax equals 0 and L equals 4. So here, funsearch has rediscovered the state of the art from 1.5 years ago, has made the step from Laporta to Johann in roughly a day of running on the machine. And if we let it run for another 1,400 generations, it has further reduced it to 88 seeds. So that's an improvement on the state of the art, albeit fairly small. I mean, we eliminated 4 seeds. That's not dramatic, but it's a proof of principle showing that this is very promising. And as promised, I can also interpret it. So this can be shown to be equivalent to the improved seeding strategy, and also requiring that t should be bigger or equal to 4. But now, okay, if you found something like a t being bigger or equal to 4, you can immediately generalize it also for other problems, which really makes this interpretable strategy so powerful. Any questions on funsearch so far?
Yeah, I have one. So
Yeah.
this specific run, that ran for 3,800 generations and then discovered the rule that is t greater than or equal to 4. Is that for a specific family, for a specific integral being reduced?
Yes.
Or
so
the triangle?
This is always for this double triangle, which Johann also used as a benchmark, and specifically for the integral with indices being 6 ones and the last one being -3.
Right. Okay.
So it's one specific integral, and of course, looking at more general integrals is what you want to do next.
Right.
But I mean, you have to start somewhere.
Yeah. Yes. Of course. For example, the t greater than 4 rule wouldn't really be applicable if there were fewer than 4 indices in the integral.
Yeah.
Right.
For better or worse, all the integrals we care about have more than 4.
Yeah. The other ones are solved.
Yeah. And I mean,
I see.
we haven't really looked into how useful this particular rule is, and what other integrals one could look at where this is helping. But the Chinese group, which I mentioned on the first slide again, in this paper, they found some ellipsis shape. So they said, pick everything in this ellipsis. And then they were able to generalize it, and they checked in their paper, also applying it to a lot of different integrals, where sometimes this was a good rule and sometimes it wasn't a good rule. But yeah, I mean, that's cool because it's cheap to try something. So it's a huge success if you have got something which works half of the cases, you get the half faster, and then you worry about the other half later. But yeah, this is something they did where they really looked at how does it generalize what they found. In their case, they looked at the simple bubble integral to find this ellipsis and then generalize it by hand to some propagator type integrals, I think up to 4 loops, planar and non-planar. So yeah, check out those papers. They're cool.
Okay, thanks.
So I have another question.
Yes.
So is the fact that Dmax came out to be 0, is that something that you could have, is it general or, so because
it's not general. No, it depends definitely on us starting with something which doesn't have a dot.
I see.
And I mean, you have to take those, I mean, you have to put some starting point. And as mentioned, it's something that I mean, Kira makes you make a guess here. And you can go from a restrictive guess to a more permissive guess if necessary. But Fire just automatically starts with the lowest value it can think of. And if that doesn't work, it increases it one by one.
I see. I see.
So then after funsearch, we looked at something more classic. And that's strongly typed genetic programming. Funsearch is in a way unconstrained. It is brainstorming using a large language model. This is trained on the whole of the internet. So any function that ever occurred in any Stack Exchange question will have the potential to pop up here. It's completely unconstrained. But this makes it also slow because it will try stuff which has no reason to work and won't work. So if we're using more classic genetic programming, we are putting in constraints, we're putting in a bias, and that makes it much faster. So typically, and the idea was behind it that now we can use it to exploit and get the same solution faster. And there's several packages for genetic programming. What we were using is DEAP. And this builds on the fact that we can write a function, a Python function or any function in terms of some syntax trees. So let's say we have a function of argument 1 and argument 2, which returns the Boolean argument 1 bigger 0 and argument 2 smaller than argument 1 plus 3. Here we could have this end as the root of a tree. Then we come here to a node bigger with leaves argument 1 and 0 and so on for this other tree. But the converse isn't true. Not everything that I build as such a tree is a valid program, because if I write something 3 plus true, this is clearly nonsense. So what I need to do is teach the program that, okay, the output of bigger is a Boolean, and you can only put Booleans into end and not numbers, and so on. And this is exactly what strongly typed genetic programming does. And then you do, again, run some kind of genetic algorithm. And this is evolving trees by essentially what's grafting. So actual trees in nature have this cool property that you can take a branch, cut it off the tree, and cut off a branch of another tree and stick the branch of one tree into another tree. That's typically done for fruit trees. But this also works for this genetic programming. So we have these syntax trees that represent some program, and we can do some crossover to replace random subtree of with a random subtree of another tree in your population. And you can also do some mutation where you replace a randomly selected subtree in something in your population by a randomly generated new subtree. So you just cut off branches and stick them into other places. And now you want to know what are the arguments here of those. And here we chose a bunch of different things. For example, this here would be what I previously called R. This is what I previously called T. This is what I previously called S, but we also put in a bunch of others just to see what happens. And then we allowed also for AND, bigger, smaller, equal, plus and minus, and also for true R marks, S marks, and the numbers between -10 and +10. And now running this for 18 generations, we again rediscovered this improved seeding strategy plus T bigger or equal to 4. So the same result as with funsearch, but we got there faster, which was what I advertised in the beginning. And here I can also show you the final tree. And I mentioned it's interpretable, but you really require some looking at it to interpret what's going on here, because those things are highly redundant. You see here, you have something and then you subtract 0. Here you have something and you add 0. So all of this is nonsense. It's highly redundant. So you really need to look at it to see what it's actually doing. But it's this intermediate complexity which makes the genetic algorithm work, because you have something which looks redundant, but then if you mutate this 0 to a 1, it's no longer redundant. Okay. Any questions on the strongly typed genetic programming?
So you said that in that case, it started, for example, with a 1, and then after 18 iteration, it got to a 0. But is that?
I mean, it could in principle happen. I don't know what.
Yeah, I mean, I'm saying it's not what happened exactly, but something on that line.
I mean, you could be tempted to say, let's prune these trees, let's cut off everything that doesn't have a function, but this would mean that you don't run the algorithm successfully, because if you do that, you disallow to mutate something that hasn't a function to something that actually then gets a function.
But just understand, how does it work? Do you give a structure of this tree, or it puts extra branches all the time and then it cuts it off, and then, but it could be infinitely long, no? So you put some.
There's a bunch of parameters. So typically you put some probability for cutting something off, probability for crossing. You put some maximum depth. You can also put a maximum size of the tree. And then you have probabilities for initializing the tree to say, okay, what's the probability to having a plus somewhere or minus somewhere, or an integer somewhere, or one of those arguments somewhere. So all of those are parameters you put into the DEAP package.
Sounds nice. And so then the way it works is that it has some branches with all these probabilities, and it checks if it's better or worse than before.
Yes, it checks better, and then you throw away the non-performing things, and you keep the top performing specimen in this population, and then you mutate the top performing specimen, and you also cross the top performing specimen. So you take one branch, say you cut off here for one non-performing top performing specimen, and you plug this sub branch here, this subtree here, somewhere into this other top performing specimen, hoping that it will be better performing than any of the two parents.
But so for each iteration is actually you do many checks with many possible trees.
Yeah,
like that.
I mean it's in generations. So you start with your initial population, and then you do this mutation and cross over, and then you have the next generation, and you just get rid of all the things that produce nonsense, and you keep the best performing ones, and it's another parameter how many top performers you keep. And then you do the next generation and do it 18 times. You find this reduction.
So is it still like something, how long would it take one generation for
So this
computationally?
whole thing took roughly a day. So here a generation took roughly an hour on a single CPU.
Nice. And this again is, you would do it for any class of integral.
I mean, here again, we did this with the
for the usual triangle
case that we used all the time.
Yes.
But yeah.
Then if you want another one, you can redo it for that one. And okay.
Yeah, I mean, this is bringing me really to the discussion at the end of generalization.
Thank you.
So quickly summarizing, these IBP reductions are bottleneck for many analytic calculations. So if we manage to solve this, we'll be able to do many interesting calculations that are completely out of reach today. And abstractly, the challenge is to pick a certain subset of equations that still allows us to solve for the desired unknowns, but being as small as possible. I told you about two machine learning approaches, one being funsearch, which is using some pre-trained large language model, and the other being strongly typed genetic programming, which restricts your arguments and builds trees of them that present programs. Both of these were able to improve on the state of the art for one benchmark integral that we always looked at. This makes this a strong proof of principle. I want to argue why this is a promising direction to further look at into the future. Now, one thing we already mentioned during the talk because of one of the questions, can you build up this system one equation by a time? So you can ask, what is the next equation I want to pick and what do I want to solve for? Make a game out of it. And then you can use fairly classical reinforcement learning techniques. So something that solves, for example, these old arcade games like Pong shown here. And this is exactly what Mao Zeng has been using in this paper from last month, using some fairly classic PPO algorithm, which works, but also has some limitations in exactly the generalization direction. But this is also something I find interesting, and working further in this direction with Justin and Francois. And then the more general question is one about generalization and deployment. So, of course, we're doing research. So once we solved a particular integral, did reduce it to master integrals, we don't care for improving it anymore. We know what the answer is. And concretely, that means we would like to have something that generalizes very well and very quickly. And these interpretable approaches I've shown you today have some promise in this direction, because you can look at them, you can interpret, okay, this is L is some equality between some of the quantities, or the inside of an ellipse, as in this paper by the Chinese authors. So you can just deploy the strategy you found. But then it's also quite interesting that here it's possible to potentially deploy the ML itself. Because if you want to deploy a strategy, you're always bound to find one solution that may be not fitting everything. But if you allow yourself to deploy ML, you might find a tailored solution for your particular problem. And the reason this is interesting is that you're not doing the calculation once in the actual IBP reduction, but typically you're doing this in finite fields. So all the state-of-the-art applications are using finite fields. You're using some numeric values, some integers, rationals for your kinematic variables. And then you're solving all of those equations in finite fields to stop them from blowing up. And then you do this bunch of times until via Chinese remainder theorem, you're able to reconstruct the rational numbers from the finite field values, and then you use some reconstruction of the polynomials and rational functions of the masses and momenta you have. So this means that you're typically running given integral reduction 10 to the 5 or 10 to the 6 different times. So you have some budget for improving this runs from one run to the next one, and thus deploy some ML. But it's of course different than, say, chess, where the chessboard doesn't change while you want to solve it. So it's not the typical ML application here. So it's a question of how quickly can you generalize? Can you generalize, or can you train with this fairly short budget for ML applications? But yeah, I think there's a lot of potential in using ML for this problem. And as mentioned before, I think there will be a lot of development and a bunch of papers coming out in the not too distant future. And with this, let me thank you.
Questions?
Yeah, maybe I have a question just to summarize. So in the approach, even with the genetic algorithm, so you start from a big set and then you reduce it. But in the approach in which you pick one equation and then you ask which other equation is going to be useful for, then it's an approach in which you start from a point and you grow the set somehow.
Exactly.
So, but do you expect that this you could do an hybrid of the two approaches, or one would be so? Which one, based on your experience, which one would you think is gonna work better for more complicated problems?
I wish I knew.
Okay, I see.
Really, I wish I knew. I mean, I'm trying to figure it out. I mean, this first paper with Matt, we worked with the restrictive approach, and now we have been, since already November, been working on this building and up one at a time. And Mao Zheng published his paper on this last month. But here, both us and Mao Zheng were using the bubble, and also our Chinese friends, they were also using the bubble. So we have been doing most of our tests, or all of our tests that I've been talking about in this paper here. We've been using this two-loop box triangle. So everybody right now is far away from state-of-the-art integrals. And it's exactly this question. I mean, how will these different approaches generalize? That's the crux here, because really nobody cares for reductions within the bubble. It's just too simple. But you need to start somewhere. You need to do some warm up, and you also want to do this warm up, or like your intuition building for cases where you can run the IBP reduction quickly. So if like one data point in the IBP reduction takes a day, you're not going to build intuition with it. You're just waiting for the non-ML step to finish.
But for example, in the case in which you can see a shape, do you think that maybe it's simpler to go towards the edge of the shape than randomly move from one point to the other? Or, in other words, would you think that there's going to be a criteria in the end of the day to determine some sort of shape using, for example, gamification?
Yes. I think there will be this criterion, and there will be some. And I mean, what Mao Zheng found really is that the algorithm found a solution where you solve the equation starting from your integral you want to reduce, going towards the integral that's the master integral. So there's a clear direction that's visible in his paper that the machine found. So that's something you could then like see and input in code in the future. And also with this ellipsis that the Chinese group found, they really looked at a certain class of integrals and saw really how does it perform for for-loop integrals, even though they found this ellipsis for one-loop integrals. And similarly, also these t being bigger or equal than 4. And this is something you can easily check. As mentioned, I mean, you have got a budget of 10,000 to 100,000 runs you anyway run in the beginning in total. So if you in the beginning you run like 10 crazy ideas that might or may not turn out to be useful, like trying an ellipsis, trying this t bigger or equal to 4, and so on, that's totally worth it.
I see. Thanks.
Thank you.
And
Yeah, I just
about
wanted to clarify, from one generation to the other, you do solve all the IBPs to see if that subset of seeds is good or not, right?
Pardon?
What?
I didn't get what you were saying.
So
From one generation to the other?
Yeah, from one generation to the other. So from one generation to the other, so you start with some seeds, and then I guess you try to improve on those seeds, right?
Yeah, I mean, in one generation from the other, we're trying with a program that selects the seeds.
Right, and then that program selects some seeds, right? And then you still need to check if it will give a good result.
Yes, exactly.
So, but in that process, in order to see if it gives a good result, you need to solve the IBP system, right?
Exactly.
Okay, okay. That's what you're saying, that okay, if it takes 1 day to solve the IBP system, then it's not.
Then you're not making any progress.
Okay.
So yeah, when typically you want something for like developing your method where solving the IBP system isn't orders of magnitude faster, slower than doing the ML part of the calculation.
Okay.
Otherwise, you'll lose a lot of time.
Right. So, for instance, that wouldn't be applicable to that result that you mentioned in the beginning of the for loop computation that was done in the context of gravitational waves. That paper by Johan and
Yeah, I mean, also in this paper, I mean, they are using this improved seeding strategy that Johan developed.
Yeah.
I think it was essentially this improved seeding strategy which made this paper possible.
Right.
But in such a case, I mean, you could put in something like a t should be equal or bigger than 4, and see whether it further improves the seeding. So you can try out various things, but this is really about the scaling. So typically in this for loop, I mean, the next calculation would be the 2SF case. So they did 1SF last year, and 2SF isn't done yet. It's the bottleneck is essentially a non-planar integral with A1 to A22.
Okay.
And
yeah, it's a lot
non-planar is typically much harder than planar. And then, okay, it's gravity, so you typically have at for loops up to 8 powers of the loop momentum in the numerator. So there's some things to do. It's a high-dimensional case. So you want to scale up to that. You don't want to start your ML approach with that. You want to start it with some baby case, build intuition, what works, how you have to tune hyperparameters, go to the next version to have something where you are on a steady trajectory. You don't want to like try out a completely new approach on state-of-the-art integrals, because then you just waste a lot of time.
Right. Yeah. Okay. Yeah. Thanks.
Thank you.
Are there more questions to Matthias? So if not, let's thank Matthias again for the great talk.
Thank you.
Yeah, thanks Matthias for giving this talk. I guess it was very timely. and appropriate for them for our consortium.
Yeah, I'm
Okay.
looking forward to hearing where you're going and what you're planning to work on in this collaboration.
Okay.
Sure.
Yeah, let's maybe keep in touch also in person sometime in the future, and then
Yeah,
and
are
then
you
we
going
learn.
to are you going to Seoul, or are you all involved?
No. During during the conference in Seoul, we'll be in Switzerland. In this, we'll have a small school about machine learning.
Which
But
will be about
more,
statistical physics, not
yeah, more, yeah.
Okay,
But,
but
okay.
yeah. Let's keep in touch.
Yeah.
Let's keep in
Okay.
touch. Yeah.
Great.
Bye. Thanks.
Bye-bye.
Bye-bye.